Hello, 9-3. Okay, so we are starting off with a warm-up. We've got Maggie and Minnie back. We have Maggie being the older sister, and we have Minnie being the younger sister. And remember, Maggie was like, I'm older. I'm the original sister. And Minnie's like, okay, I guess that makes me the new sister. Anywho, in this situation, we have the two of them sharing bunk beds. Now, we know Maggie and Minnie are similar to each other because they are shrunken down or enlarged versions of each other. Other than everything being shrunk to create Minnie to be exactly who she is, all of their proportions are similar to each other. Now, Minnie and Maggie have these bunk beds, and we have the measurements of the bunk beds here. And Minnie's upset because she goes, hey, even though I'm similar to Maggie, my bed isn't similar to Maggie's. I want to know if she's right. So pause this video in like 2 seconds and see if you can figure out, make a conclusion if the two beds are similar to each other in the same way Maggie and Minnie are similar to each other. You can use scale factor. That can try and be your little hint to get going. But you have a few minutes to try that out. Pause the video. Okay, welcome back. So hopefully you gave it a go. And a couple of things that we might have noticed is that they're actually not similar. Now, whether or not you actually came up with some reason as to why they're not similar or why, that's okay. We're going to talk about it right now. Now, just a reminder, when we talked about Maggie and Minnie being similar, we talked about scale factor. And their scale factor for each of their measurements was consistent. So let's say, I don't remember what the numbers are, but let's say Minnie was half the distance between, for Maggie, the scale factor was 0.5. That means her measurement between her feet is going to be half the size of Maggie's. Her height should be exactly half the size of Maggie's. The distance between her antennas should be exactly half the size of Maggie's. Every single measurement should be always the exact same scale factor of 1/2. Now, when we take a look at the beds, we have two measurements. We have how long the bed is, and we have how wide the bed is. So I'm going to find the scale factor of both how long, the length of the bed, and the width of the bed. So I'm going to label them just so that we're super clear. If I went ahead and calculated the width of the bed and I calculated its scale factor, we know scale factor is always going to be new over original. Now, since we deemed Minnie as the new version, we should then also expect that the top bed is going to be the new of the original, which is going to be the bottom. So we're going to take those two measurements of the width, so 65 and 150, and use them to find my scale factor. Okay? Now we could plug this into our calculators and get a decimal, or we can figure out what it is as a fraction and reduce it. Both are totally acceptable. I'm going to do both, just for the sake of practicing. I know that the top and bottom here, that's the wrong number here, are both divisible by 5. Okay, because they both end in either 0 or 5. 65 divided by 5 is 13. I could think of, well, okay, in 50, there's 10 5s. So in 65, there's going to be 3 more 5s. And I know that 150 divided by 5 is going to be 30, because if I just ignore the 0, 15 divided by 5 is 3. So I could add that 0 back in when I'm doing that mental math. I also can see in my calculator that that's also going to be 0.43 repeating. Doesn't quite matter because we're just comparing to see if our scale factors are going to be consistent here. Now, I'm going to do the exact same thing with scale factor, but now I'm going to do it for length of the bed. Same idea, scale factor is new over original, which is going to be 200 over 200. Hey, that's just 1. What we might notice that the scale factors are different from each other And if I have different scale factors, then I know that the beds aren't going to be shrunken down or enlarged versions of each other. They are two separate sets of measurement that don't necessarily have much to do with each other. So Minnie's right. She is justifiably upset because the scale factors are going to be different for each dimension. So now what? Let's talk about what it means to be similar. Now, to be similar, we need to meet kind of two conditions. Condition number one, that all of the corresponding sides must have the exact same scale factor applied. So it's not just the same scale factor the same, but it's for every single set of corresponding sides. So remember, corresponding sides would be like I'm measuring height with height, or length with length, or width with width, or biggest length with biggest length, and smallest side with smallest side. So that's what corresponding sides mean. I'm talking about the same measurement, but the scale factor has to be the same. If they have that, then we typically do say that they are similar to each other. Oops, that's a highlighter. Similar to each other. Except there is one more condition. So that first condition, that highlighted yellow condition we have. But the second condition is that their corresponding angles are equal. So what does that mean? Well, let's walk through a little bit of a mini example. So a shape that we all know and love, the square. Ooh, a square. Now in a square, I know all four sides are equal to each other. And I'm going to just pick a number. Let's go with 1, make this really easy. All of these side lengths are 1, let's say, centimeter long. Now if I wanted to draw a similar shape, I would need to have a similar or the same scale factor applied to every single side. So let's say I'm going to do a scale factor of 2. Since that number is bigger than 1, it'll be an enlargement, and every single side will be twice as long. So if this was all 1 by 1 for a square, the new square I'm going to draw is going to be 2 by 2. And now I know this shape is going to have the same scale factor applied to each one, because to get from 1 to 2, I have a scale factor of 2. From 1 to 2, scale factor of 2. 1 to 2, scale factor of 2. I need another color. 1 to 2, scale factor of 2. So condition 1 is met. Condition number 2 is that I need all of my angles that are corresponding to be equal to each other. So that's not what I wanted. There we go. This angle in a square, actually all 4 angles in a square are 90 degrees. And that's pretty great. So is this one. So these two squares are considered similar to each other because not only do they have the same scale factor applied, but all of their corresponding angles are also equal. Now, why the second condition is really important? Because imagine, instead of having a square that I drew a rhombus. Now, a rhombus is a 4-sided shape in which all 4 sides are equal, but their angles are not all 90 degrees. Okay, specifically that they have 2 pairs of matching angles here. Now, if I was looking at my original square that I drew, and I only looked for the first condition that the scale factors would have to be the same for every pair of corresponding sides, I'd be fine, right? It matches. But visually speaking, I could tell these shapes aren't similar because A, they don't look like each other. They don't look like enlarged or shrunken versions. But B, the angles do not match. This angle here and this angle here, they're going to be the same, but they're both not 90 degrees. So both conditions must be met for those two shapes to be considered similar. We are moving on to the first example here. So I am told that these two shapes are similar because remember that squiggle implies similarity. Now, there's a lot of information that we get from how these two shapes are named because the order of that name will tell us a lot. So, this letter A is the first angle of my shape, or the first vertex of my shape, and so is this angle W. It's the first vertex of this shape. knowing that these two are similar because of that squiggle symbol between the two names of these two shapes will indicate that those two angles will be equal to each other, or they'll be corresponding with each other. Similarly speaking, angle B and angle X will also be corresponding to each other. And angle C and angle Y will be corresponding to each other. And angle D and angle Z will be corresponding to each other. So the order that we actually gave that name in tells us a lot of information, knowing that these two shapes are already similar, because that's what the symbol tells us in between them. Now, I know the first part of this says, what conclusions can we make about the side lengths? But I'm going to actually jump to what conclusions can we make about the angles. Well, we know in similar shapes, two bits of information are clear to us. Thing number one is that if we found the scale factor for every single pair of corresponding sides, we'd get the exact same number. The second thing we know is that all corresponding angles will be equal. So what conclusions can we make about this graph? Well, since all corresponding angles are equal, then I know that angle A, since it's corresponding to angle W, angle A, that measurement, will equal the measurement of angle W. And angle B will equal that measurement for angle X. And angle C will equal that measurement for angle Y. And angle D will equal that measurement for angle Z. So knowing that they're similar and knowing that the name tells me they're corresponding angles, I can use the information I know to tell you those angles are going to be equal to each other. Just a couple of reminders. Remember, angles are points, or angles are named based on points of their vertices. Those points are all using capital letters. So please make sure all of your angles are identified using capital letters. Okay, what other information can we talk about? Well, remember, to be similar, you have to meet two conditions. Condition number one, let's say we'll go in other order, but one condition is that all of the corresponding angles are equal, and we kind of dealt with that. But condition number two is all the scale factors of corresponding sides will be the same. So I'm going to write that. All pairs of corresponding sides will result in the same scale factor. Okay. If you have a highlighter, just for funsies here, I'd like you to take a moment, or just even like a pencil, and somehow indicate which sides are going to be corresponding to each other. Now, this information, the way that the shapes are oriented, it might be a little bit obvious to us which ones are going to be corresponding. So I know A, B, and W, X are going to be corresponding. But the other way that I can see that is those two letters side by side in the name, because the name's order matters a lot, will also tell me what I've got, which ones are corresponding. So A, B, and W, X, corresponding. B, C, and X, Y, corresponding. C, D, and Y, Z, corresponding. Now the last one, D, A, and ZW, also corresponding. So I can see that there are 4 pairs of corresponding sides. Now, if I wanted to find the scale factor for any single part of this shape, I know the scale factor is going to be the same anywhere. And the scale factor is always talking about new divided by the original. Now, it doesn't actually tell me which one's the new and which one's the original, so I kind of have the freedom to make that up. So out of my 2 shapes here, I'm going to just say this small one's the new and this big one's the original. Now, it doesn't actually matter which one I deem as which, but I just need to make sure I label it so that I can have my kind of scale factor be consistent based off those labels. So scale factor is new over original. And I know there's no numbers here, but I'm not going to use numbers because I don't have them. I'm going to use the names of those side lengths. Now, luckily, we all did Unit 6, our geometry unit, where we talked about how to appropriately name sides. So this side length that I've circled here, AB, or starts at A and ends at B, will be called side length AB. It's just a line segment. So I'm going to call it AB just as I would have. Now, for my scale factor, AB being my new side will be at the top, and its corresponding original side will be at the bottom. And I'm going to name it in the same way, WX, because they're both line segments. And I'm going to do this for every single pair of sides, because every single pair of sides will result in the exact same fraction. So whatever number AB is divided by whatever number WX will give me the exact same fraction of whatever number BC is, as long as I divide it by whatever number XY is, because our scale factors, that's how I would find them, but their scale factors are going to be the same for every single pair of corresponding sides. So CD will be the same as CD over YZ will give me the same scale factor here, and the last one as well. Now, I don't totally care what order we write these in, like A, D, or DA. I just want to be consistent. So if I'm taking a look at D from the right side of that line segment to A to the left side, then I kind of like doing the same thing for my other one, Z to W. Okay. Now, this is what I can say about all of my corresponding sides. They will result in the same scale factor, so I could say those proportions of sides will all be equal. Okay. Now, instead of being told we have shapes that are similar to each other, we want to figure out if the shapes are similar to each other. I have two rectangles here. Remember, for things to be considered similar, I need to have every single proportion, every single scale factor of corresponding sides has to be equal, and all of the angles have to be equal. But as soon as I don't meet one condition, automatically I'm not considered similar. So I could just go through conditions one at a time, and as soon as I see something like some sort of discrepancy, I don't have to proceed further. In these rectangles, I'm going to start with scale factor. Okay, so my first condition we talked about was scale factor, so I'm going to do that. And I'm going to label these rectangles as new and original. Again, kind of choosing which one's which, but just so that I'm consistent with it. Okay, I'm also going to, just for my own sake, highlight sides that are going to be corresponding to each other. Now in a rectangle, remember I have two pairs of matching side lengths. So that 18 at the top, AB, that side length, is actually going to be identical in measurement to side length DC. And same with ZY being identical in measurement to WX. So I'll notice that any of the blue measurements will correspond or should correspond with any of the blue measurements from each rectangle. And same orange with orange. I could also very happily go ahead and label the missing sides of these rectangles, because I know that rectangles have two pairs of matching sides. Okay, so I have scale factor that I'm going to tackle, and I'm going to do one of them in orange. So I'm going to look for scale factor for my orange sides, and I'm just going to tell you, instead of saying SF every single time, I'm going to identify scale factor as new over original, and then I'm going to use the proportion, kind of like we did before, because I don't want to write SF many times. It might get a little bit confusing. So what I mean by that is if I'm looking at these two measurements, I'm going to, instead of saying SF, I'm going to write AB over WX. So I'm very specific about what side lengths I'm talking about and the ratios between them. That gives me 18 over 25, and I can plug that into my calculator. Beep, boop, bop, and get 0.72. Now I'm going to do the same thing with my blue side. So I know scale factor would be new over original, but again, if I just write SF, it might be a little bit confusing about which scale factor I'm talking about. So I'm going to go and say, well, that's side AD over side WZ, and plug in those numbers. 36 over 45, beep, boop, bop, plug it into my calculator. I get 0.8. Now the scale factors are not the same. Because these scale factors are not the same, the rectangles are not similar. So I'm going to write that. The scale factors are not the same for each pair of corresponding sides. So the rectangles are not similar. All right, in this last example, we have two octagonal garden plots. Octagonal just means that we have 8 sides. And the two garden plots are similar to each other, which means we know all of the angles are going to be equal, all the corresponding angles, I should say. And we also know that the scale factor between every pair of corresponding sides is also going to be the same. Given that information, we can actually find missing lengths. Now, this question is essentially what we did last section. This is exactly what we did in 9.2, except now we have the added bits of information of like making sure that our shapes are similar first before we can proceed. Every single question we gave you in 9.2, they were similar. You didn't even have to think about it. You just went ahead and did it every single time. 9.3 is like, okay, now I have to think about it. Now I have to make sure they're similar before I proceed with actually finding my missing lengths. So, we're told that they're similar, which means we could do all of the things that we did before in 9.2 to find the missing side lengths. So we want to find side length GH. Think about which one's corresponding to it. Yep, you've got it. It's PQ. Now, to be able to find those missing lengths, I need to know the scale factor first because I know the scale factor is going to be the same everywhere because I know they're similar. So I want you to find 2 sides, one on each of these shapes that I could use to help me find the scale factor. Did you do it? And if you did you get these ones? AB and IJ. Well, if you did, props to you. So our steps are going to be to find the scale factor first. Scale factor we know is new over original. It doesn't tell me which shape is new and which one's original, so I'm going to label them are. So I'm going to go new for the first, original for the second. If you had swapped them up, you get a different scale factor, but you get the same final answer for your side lengths, so you would be marked correctly no matter. That's all good. And I'm going to go new over original. That's 5.4 over 8.1. Now, if I wanted to practice doing this mental math-wise, I can go ahead and do that. I know 5.4 over 8.1. I don't like decimals in there, so I'm going to times top and bottom by 10. And when I do that, I'm going to get 54 over 81. And I know both of those numbers are divisible by 9. So I'm going to go ahead and do that. So divide top by 9, divide the bottom by 9. Well, 9 goes into 54 6 times, 9 goes into 81 9 times. Ooh, and that can reduce even further to give me 2/3. Now, technically, some of you might be saying, okay, Ms. T, can I not just please plug this into my calculator? Well, if you were to plug this into your calculator, you would get 0.666 repeating, which you might round to 7. It's always best to use non-rounded values when possible, just because then you'll get the most accurate final answer as a result. It's not necessarily wrong. It might just end up with a little bit of a communication error when you simplify, so just kind of be mindful of that. Okay. Remember that you could still use your calculators to figure out what top and bottom when I times by 10 get me, or what top and bottom when I divide by 9 get me. So you could still use your calculator to help reduce that fraction and make those steps a little bit easier. Okay, once we find the scale factor, then we're going to use the scale factor to find the missing sides here. So I know my scale factor is 2/3. and that was new over original. And I'm going to plug in the values for GH over PQ. Now, again, I'm just showing you this saying like, okay, I know that these are similar, so proportion of any set of corresponding sides is going to equal to that scale factor. But you are more than welcome to just start here and go GH over 32.4. Okay. And we are going to solve for GH right now. It's being divided by 32.4, so I'm going to multiply both sides by 32.4. Notice I'm multiplying the top of each fraction by 32.4 because that's what allows me to cancel the top with the bottom. If I multiplied the bottoms by 32.4, then 32.4 times 32.4 doesn't cancel out. That gives me some big number. What's 32.4 times 32.4? Well, that's 1049.76. It doesn't cancel out at all. So it's really important that I'm multiplying the top of both fractions because that is what allows me to cancel that top with the bottom. All right, I can plug this into my calculator. So 32.4 times 2, well, that is a highlighter. Well, that gives me 64.8. And I still have that over 3. And when I plug that in divided by 3 in my calculator, I get that final answer of 21.6. Now, even though scale factor doesn't have units with it, remember side lengths do. All of these side lengths have been measured in meters, so I need to make sure my meters are indicated. Okay. Try the last one on your own. We're just using the exact same scale factor to find another side length. Pause the video, try it out. Did you pause it? Well, I hope so, because I'm going to do it now, and we're going to see if we get the same thing. So I have 2/3 is still my scale factor, and I want new over original. Well, I'm looking for those corresponding sides, so I'm looking for side NP, and that's this one here, and this corresponding side would be FG. Okay. And I'm going to make sure that I plug in new over original. So I have the highlighter again. Okay, 27 over NP. And now I can solve accordingly. Because my unknown's in the denominator, I'm going to want to cross multiply. So I'm going to go 2 times NP is equal to 3 times 27, which is 81. And then I'm going to divide both sides by 2 to get NP alone. And I'll find out that NP is equal to 40.5 meters. Okay, quick summary of this lesson. We learned that to be considered similar, you need to meet 2 conditions. The scale factor for every pair of corresponding sides has to be the exact same. And all of the angles, the corresponding angles, also have to be equal to each other. They don't get factored up and factored down. They are exactly the same if these shapes are similar. We also talked about the order of a name in 2 shapes that were given to be similar is very informative to us. It tells us the order in which angles are going to be similar to which other angles. It tells us which side lengths are going to be proportional to which other side lengths. We also kind of at the end figured out that, hey, I've been using the information in an assumption that things are similar to begin with, but I now know that I can continue to use that as long as I double check that it's either told to me somewhere that it's similar or that I've checked that it's similar, and I could use that scale factor to find missing side lengths. And that is it for 9.3. We are going to have that 9.1 to 9.3 quiz on Wednesday. So if you can please make sure that you complete this homework, you ask me questions if you have them, and we could touch base tomorrow. That would be great. All right, goodbye.